हेलो स्टूडेंट्स जो हमारा लास्ट टॉपिक चल रहा था दैट इज़ फर्स्ट ऑर्डर रिएक्शन। तो फर्स्ट ऑर्डर रिएक्शन का ये एग्जांपल लिख रखे हैं। N2O5 और N2O जो होती है उनकी जो डिकम्पोजिशन होती है दैट इज़ ऑल्सो एन एग्जांपल ऑफ फर्स्ट ऑर्डर रिएक्शन। ओके, दिस इज एन एग्जांपल लाइक N2O5 is giving out 2NO2 plus half O2. Okay, and this is the initial concentration, that is 1.24 into 10 to the minus 2, and after 60 minutes, that means after 60 minutes the concentration remains 0.2 into 10 to the minus 2 mole per liter. And now we need to calculate the rate constant. This is the first order reaction. Okay, so this is the formula for first order reaction: log a1 upon log a2, that means first concentration second concentration equal to k t2 minus t1 upon 2.303. Okay, so k will be, we need to calculate k, and k will be 2.303 will be multiplied this side, and t2 minus t1 will be divided this side. Okay, 2.303, this is the rearrangement of this formula. Then after putting these values, 2.303, the time is taken was 60 minutes. Okay, and let's consider the initial concentration is given and initially time was 0. Then after log initial concentration 1.24 into 10 to the minus 2, and the final concentration 0.2 into 10 to the minus 2, and calculating these all values we get the value of k as 0.0304 per minute. Okay, here minute is given, so the k will be in the per minute. Then after this is a question. Then after, if the first order reaction is not given in form of concentration but it is given in form of pressure, that is gas is given in the reactants. Okay, then initially at time 0 we consider that the pressure of this reactant is pi. I means initial. Okay, and as no product is formed, so pressure of these products is 0. And after time t, let's consider that the pressure decreases by x, and these two products will have pressure x and x. Okay, then after pi is the initial pressure at time 0. Now adding these value we get the total pressure of this reaction mixture. Okay, total pressure will be pt equal to pi minus px plus x, all the total sum of these all, pi minus x plus x plus x. Okay, it becomes pi plus x. Okay, x say x cancel, and then after the value of x is pt minus pi. Okay, pt minus pi, and then after, suppose this pressure, that means the pressure at time t, instead of writing it as pi minus x, we write it as pa. Okay, pa, then pa will be pi minus x, pa will be pi minus x, and the putting the value of x, that is pt minus pi, we get 2 pi minus pt. Okay, so putting these values in the first order reaction equation, k is equal to 2.303 by t log initial pressure and final pressure. Initial pressure is pi and final pressure is pa, that is 2 pi minus pt. Okay, this is the first order reaction for pressure. Then after half life of first order reaction, half life is the time in which the concentration of reactant becomes half, that means half of the reactant converts into product, that is the half life of a reaction. As we know, for a first order reaction, k is equal to 2.303 by t log a naught upon a. Okay, this is the first order reaction, and at half time, that is the concentration of initial concentration of reactant becomes half. Okay, a naught by 2 means half of the reactant is converted into product, so this value becomes a naught by 2. Okay, putting these value we get t is equal to t half, that means half life, and a is equal to a naught by 2, and it comes out to be k equal to 2.303 t half log a naught upon this value a naught by 2. Okay, it comes out to be a naught say a naught cancel, and it comes log 2. Okay, and the value of log 2 is 0.3010. 2.303 multiplied by 0.3010 becomes 0.693. Okay, by k. One more thing, half life is independent of you can see that T half does not depend upon the concentration. That means you can say that half life is independent of the concentration or the initial concentration of the reaction. One more thing you can write that the first order reaction never ends. That means फर्स्ट ऑर्डर रिएक्शन जो होती है वो कभी कंप्लीट नहीं होती. ठीक है. अब फर्स्ट ऑर्डर रिएक्शन हैज़ के इक्वल टू 5.5. दिस इज अ क्वेश्चन. Into 10 to the minus 14 per second. Find the half life. We know that to calculate the half life we don't need what concentration. Okay. First order reaction T half will be 0.693 by K, and the value of K is 5.5 into 10 to the power minus 14, so it comes out to be 1.26 into 10 to the power 13 second. Show that in the first order reaction time required for the completion of 99.9% is 10 times of half life of the reaction. That means 99.9% reaction has been completed. Okay, and let's see how to put these in the rate equation. This is the k equal to 2.303 by T log A naught upon A. Log A naught upon A is the rate equation, and the value of A will be, as the 99.9% of the reactant has converted into product, so we write here the remaining reactant. Okay, and the remaining reactant will be initial concentration minus this is for 0.999 is the fraction of A naught that is converted into product, so the remaining will be 0.001. Okay, 0.001 A naught, that is A naught. If we solve this we get 0.001. okay, A naught. So it comes out 0.001 means 10 to the power minus 3. Okay, 10 to the power minus 3 is in denominator, and to get into numerator it comes out to be 10 to the power plus 3, or you can say 3. Okay, using this calculation we get 6.909 by K. Okay, 6.909 by K, and for the half life we know 0.693 by K, and this is 6.9, 0.6, and this is 6.9, so it is 10 times of this value. So we can say that by dividing T divided by T half we get 6.909 divided by 6.93. K will be cancelled and it comes out to be 10. Okay, it comes out to be approximately 10. So we can say that T half is 10 times of 99.9% of a first order reaction. Then after pseudo first order reaction, what is pseudo first order reaction? Actually pseudo first order reaction is a reaction in which both the two reactants are there and both the reactants participate in the reaction, but one of the reactant is in very excess amount. Excess amount means there is no considerable change in the concentration of that reactant. For example, if we take we are making a solution and consider that as a reaction. Okay, and in that solution we use 10 liter 20 liter of water and 1 gram half gram of sugar. Okay, and we are making the solution. So in that case the concentration of water remains almost constant. Okay, there is no considerable change in the concentration of water, but sugar particles dissociate. One more example is hydrolysis of ester. In this reaction and the water is actually taking part in the reaction, but water is in excess amount. Like we are taking 10 mole 30 mole of water and 0.01 mole of CH3COOH, so there is no considerable change in the concentration of, like we can take, if we are taking 0.01 molar, okay, of this and 10 molar of this, and after completion of reaction this is a T0 and it is T, it becomes 0 and it becomes 99 sorry 9.99. okay, so these values are almost same. Okay, there is no considerable change in this value, but this is the considerable change. So we can say that this reaction actually depends upon the concentration of this reactant only, that is CH3CO. Actually, it is not CH3COOH, it is CH3COOC2H5. Okay, CH3COOC2H5 plus H2O, it gives out CH3COH plus C2H5OH. In this reaction, water is taken in excess. Okay, and the rate will be, as I have already told you, the rate will depend upon the both K dash CH3COO C2H5 to H2O, but the H2O's concentration is almost constant, so we can take one more constant, that is K, will be equal to multiplication of these two constants, K dash and H2O. So the rate will be uh, K will be K dash upon H2O, K into CH3COO C2H5. Okay, and this is also called K prime. K dash is also called K prime. Okay, so in this way we can say that the rate of reaction depends upon the 1 power of the concentration of this reactant only. So it is not actually the first order reaction, but it is considerable to be first order reaction. So we call it as a pseudo first order. Pseudo means fake. Okay, pseudo first order reaction. And mostly in the hydrolysis of most of the substances, pseudo first order reaction is there. Okay, like the hydrolysis of this sugar particle, hydrolysis, further hydrolysis of this, time required to decompose SO2, hydrolysis of methyl acetate in the aqueous solution is also a pseudo order reaction. Okay, then after we do numerical, that is time required to decompose SO2Cl2 to half of its initial amount is 60 minutes. Okay, time required to decompose SO2 into half of its initial amount, that means this is the half life. If the concentration is of first order, calculate the rate constant. For half life, the formula is 0.693 by K. Okay, 0.693 by K, and you can calculate using that formula into this. Then after temperature dependence of rate of reaction, okay, we know that the rate of reaction increases with increase in temperature. Generally, rate of reaction increases with increase in temperature, and with every, it is considered that it at every 10 degrees Celsius or 10 Kelvin, there is the rate of reaction almost doubles. Okay, at 10 degrees Celsius, rate of reaction almost doubles. Okay, and it is given by Arrhenius, and the equation is called Arrhenius equation. And Arrhenius equation is K, rate constant, A into e की power, E is exponential raised to the power minus EA. EA is the activation energy, we will discuss it about. Okay, then after divided by RT. R is universal gas constant, T is temperature. What is A? A is Arrhenius factor or frequency factor or pre-exponential factor. Okay, it is called Arrhenius factor, frequency factor, or pre-exponential factor. Means you can say how frequently molecules are collide together and making product. For that, this constant is taken, and this constant is specific for every reaction. Okay, for every reaction this constant is specific. Then after gas constant, okay, I have already told you about this. Then after, consider this is a reaction, H2 plus I2 is giving out 2HI. Okay, in this reaction, how the reaction occurs? First of all, hydrogen and iodine molecules approaches towards each other, and a start of formation of bond between hydrogen and iodine takes place, and dissociation of this bond HH and II takes place, and this complex or this intermediate compound is formed. Okay, and then after, this is quite unstable, and then after it make the reaction proceed towards the product, that is HI. Okay, HI. This can be understood by a graph. Okay, and the graph is like this is a reactant, and we are taking H2 and I2. Okay, and whenever the energy is given to them, their energy increases, and the unstable complex is formed at this peak. Unstable complex is formed at this peak, that is intermediate. And after the formation of that, as it is unstable, it reaches to the product. Okay, it leads the reaction towards the product like this. Okay, and during the formation of product, energy is again released. First of all, reactant consumes some energy and reaches up to this intermediate, and then after it releases energy to make product. One more thing, this is the actual energy at which a reactant start reacting. Okay, initially this reactant is not able to react. Okay, but after reaching this energy, like अगर हम मान लो कोई माचिस जला रहे हैं, माचिस की तीली, तो उसमें शुरू में हमें उसको हीट देनी होती है. अगर हम कोई पेपर जला रहे हैं उसमें हमें शुरू में हीट देनी होती है, बट as soon as it reaches to that energy that at which it starts burning. Okay, so then after it releases energy and form the product, that is in case of these papers etc, smoke. Okay, so this is the energy, or you can say in the form of potential energy, and this is the energy at which the reactant starts reacting, and this is called threshold energy. Okay, threshold energy is this energy, this is the gap between 0 to this, and the energy required by the reactant to reach the threshold energy is called activation energy. कोई भी रिएक्टेंट जब तक एक्टिवेशन एनर्जी तक नहीं पहुंचता तब तक वो रिएक्शन स्टार्ट करता ही नहीं है. ठीक है, and once it reaches to the activation energy, then after it starts giving product. Okay, this is the energy of the product, and this is the energy of the reactant, or you can say internal energy, and this is the enthalpy change, that is the overall energy released during this reaction, delta H. It is enthalpy change. Okay, so threshold energy is the minimum energy that molecule need to have in order for a reaction to take place, and activation energy is the minimum energy required by the molecules to reach the threshold energy. Okay, it is the minimum energy required by the molecules to reach the threshold energy. One more thing, this is the internal energy, this is the activation energy. So the sum of this internal energy and activation energy is called threshold energy. Threshold energy is the internal energy of molecule plus activation energy. Okay, and this is the enthalpy change, that is the final enthalpy change during the reaction. Okay, we also use Maxwell's graph. Okay, and what does Maxwell's graph say? It actually talk about the kinetic energy. That means the molecules are continuously striking to each other by their kinetic energy. So he discussed about that kinetic energy. He considered that Ne upon Nt. Ne is the energy of the number of molecules with the energy E. Let's consider the energy of the molecules is E, and Nt is the total number of moles, that is it is the fraction of molecules which are moving to give products. Okay, and this is the graph. In this graph you can see that this is the fraction of molecules, this is most probable kinetic energy. What is this? Actually this is the kinetic energy, and you can see this graph that initially only a few molecules were there. That means a fraction of molecules were there which is having very less kinetic energy, and very few molecules are here which are having very less kinetic energy. But in this peak you can see that the kinetic energy in between this value and this value is like this. Okay, so this is the kinetic energy that most of the molecules are having. Okay, about this kinetic energy, and this kinetic energy that most of the molecules are having is called most probable kinetic energy. Okay, you can take the example of a class. एक क्लास में क्या होता है, कुछ ब्रिलियंट, देखो यहाँ पे काइनेटिक एनर्जी बहुत ज़्यादा है, यहाँ काइनेटिक एनर्जी बहुत कम है. हमने ज़्यादा काइनेटिक एनर्जी को ब्रिलियंट स्टूडेंट्स मान लिया, बहुत कम काइनेटिक एनर्जी को मान लिया कि जो क्लास में नेल स्टूडेंट्स होते हैं. तो ब्रिलियंट स्टूडेंट्स भी बहुत कम होते हैं. ओके, फ्रैक्शन ऑफ मॉलिक्यूल्स जैसे यहाँ पे कम है, यहाँ भी फ्रैक्शन ऑफ मॉलिक्यूल्स कम है, ब्रिलियंट स्टूडेंट्स कम है, लेकिन एक एवरेज जो मार्क्स लेने वाले स्टूडेंट्स होते हैं वो सबसे ज़्यादा होते हैं क्लास में. सो दिस इज द एवरेज काइनेटिक एनर्जी, एंड दिस इज कॉल्ड मोस्ट प्रोबेबल काइनेटिक एनर्जी दैट मोस्ट ऑफ द फ्रैक्शन ऑफ मॉलिक्यूल्स आर हैविंग. ओके, अच्छा ये तो था सिंपली एक ग्राफ. अब कई बार क्या होता है, हमें कंपेयर करना होता है टेम्परेचर डिफरेंस के ऊपर, जैसे कि हमने सेम रिएक्शन है, पहले उसको टी टेम्परेचर पे लिया एंड देन आफ्टर वी हैव टेकन इट एट T+10 डिग्री। ओके, एक बार मान लो हमने 50 डिग्री पे लिया तो एक बार 60 डिग्री पे ले लिया, तो क्या हुआ देखो ये ग्राफ सेम है, फ्रैक्शन ऑफ मॉलिक्यूल्स। एक बात और याद रखना, एवरेज काइनेटिक एनर्जी ऑफ द मॉलिक्यूल्स रिमेन्स सेम ऑलवेज। जैसे कि ये सारे मॉलिक्यूल्स हमने कंसिडर कर लिए और उनकी काइनेटिक एनर्जी निकाली, और ये सारे कंसिडर करके कर लिए उनकी काइनेटिक एनर्जी निकाली, वो दोनों की एवरेज काइनेटिक एनर्जी दोनों की सेम आएगी। ठीक है, किसी भी एक पर्टिकुलर रिएक्शन में वो सेम होती है। तब देखो इसमें काइनेटिक एनर्जी यहाँ ज़्यादा है, ठीक है, तो यहाँ आके कम होगी, इसमें यहाँ कम है, तो ओवरऑल इसमें इस ग्राफ में आगे फर्दर जाके काइनेटिक एनर्जी ज़्यादा होगी, तो ओवरऑल जो काइनेटिक एनर्जी आएगी वो एवरेज काइनेटिक एनर्जी वो दोनों के लिए सेम ही, दोनों केसेस में सेम रहती है। ठीक है, अब यहाँ देखो जब T+10 था तो जो एक्टिवेशन एनर्जी है कंसिडर करो, ये है एक्टिवेशन एनर्जी, मतलब इससे पहले पहले जितने मॉलिक्यूल्स है वो रिएक्शन कर ही नहीं पा रहे क्योंकि वो एक्टिवेशन एनर्जी तक नहीं पहुंचे। लेकिन यहाँ पे ये एक्टिवेशन एनर्जी है जिसपे ये सारे मॉलिक्यूल्स नीचे वाले और ये ऊपर वाले मॉलिक्यूल्स पहुंच गए। तो अगर हम इसमें देखें तो देखो इसमें जो ये एरिया है, दिस इज द फ्रैक्शन ऑफ मॉलिक्यूल्स ओके एट टी टेम्परेचर, एंड अगर पूरा इस एरिया को कंसिडर करें, दिस इज द फ्रैक्शन ऑफ मॉलिक्यूल in this temperature, and it is this area is almost double to this area, so we can say that T+10 the reaction rate becomes double, क्योंकि double of the molecule, almost double of the molecules are reaching to the activation energy at 10 degree rise in temperature. Okay, so this is all explained in this with this graph. Then after if we come back to Arrhenius equation, k is equal to a e raised to the minus ea upon rt, okay, and taking log in both side, natural log ln k is equal to ln a e raised to the minus ea upon rt, and ln a plus log a plus log b becomes log a to b becomes log a plus log b, that is ln a plus ln e to the power minus ea upon rt. Okay, and this becomes ln k ln a, ln cancel out this e and it comes out to be minus only minus ea upon rt. And if we compare this equation with y is equal to mx plus c, we get this is the y coordinate and this is the x coordinate. At x coordinate we take 1 by t, okay, and e minus ea upon rt will be m, that is slope, and the graph becomes ln k, this is the y coordinate, 1 by t is the x coordinate, because it's a equation of straight line and the slope is negative, so the line comes out to be like this. Okay, and this is graph of ln k versus 1 by t in Arrhenius equation, ln a, this is the slope, minus ea upon r. Then after, if two different temperatures are given, like recently we have seen that one temperature was t and another temperature was T+10, okay, like that two different temperatures are given, then we use Arrhenius equation as, like, for first temperature, that is T1, we take it as ln k1 is equal to minus ea upon rt1 plus ln a, and for second temperature T2 it comes out to be ln k2 is equal to minus ea upon rt2 plus ln a. This is the second equation. Okay, and subtracting first equation from the second equation, we get ln k2 minus ln k1 minus ea upon rt2 plus ln a minus ea upon rt2 plus ln a, minus this equation minus ea upon rt1 plus ln a. This negative and this negative symbol becomes positive, and this positive, this negative becomes negative, so ln a cancels out this ln a, and the equation becomes ln k2 upon k1 is equal to ea upon r is common, 1 by t1 minus 1 by t2. Okay, and rearranging this equation we get log in form of in the earlier equation it was natural log, and we convert it into log, we get log base 10. It becomes we need to multiply it by 2.303, or this 2.303 comes out in this side as the denominator. EA upon 2.303 r 1 by T1 minus 1 by T2. So log K2 upon K1 becomes EA upon 2.303 r T2 minus T1 upon T1 T2. Okay. Then after a question is there, that is the rate constant for a reaction at 500 Kelvin and 700 Kelvin are 0.02 per second, 0.02 per second and 0.07 per second. That means two rate of reactions are given. First one, rate constants are given, that is log 0. We put these values in the equation. Log K2 upon K1, K2 is 0.07 and K1 is 0.02. Okay. EA 2.303, the value of R is 8.314. T2 minus T1 upon T1 T2, temperatures are given as 700 and 500. T2 is 700 Kelvin and T1 is 500 Kelvin. Okay, and we put this value here and we get the value of EA as 18230.8 joule, and the value of K is A is can be calculated using this equation. K is equal to A e raised to the minus EA upon RT, and we can take any of this case, that is we can take 0.02 per second at 500 Kelvin, or we can take 0.07 per second at 700 Kelvin as the rate constant. Okay, any of the values we can take and we can calculate the value of A. So we are using the first value, that is 0.02 at 500 Kelvin equals to A e raised to the minus 8230.8. This is the value of activation energy. R is 8.314 multiplied by 500 Kelvin is the temperature. That means it is divided by this value and it comes out to be 1.61. So this is a numerical on the basis of Arrhenius equation. Then after, the next topic is effect of catalyst. Effect of catalyst. A catalyst is a substance which generally increases the rate of a reaction without itself undergoing any permanent chemical change. That means like this is a reaction in which MnO2 is a catalyst. Okay, MnO2 increase the rate of reaction, that is but it does not dissociate into like it actually participate in the reaction, but after the final reaction MnO2 is found to be in the form of Na2 itself. Okay, MnO2 itself. Okay, that means there is no permanent chemical change in the catalyst takes place, it only increases the rate of reaction. Okay, and if a catalyst or a substance decreases the rate of reaction, it is called negative catalyst or inhibitor. It is called negative catalyst or inhibitor. Suppose this is the reaction coordinate, that means reaction is proceeding. This is the potential energy. Okay, so this is the reactant, and when the reaction takes place without the presence of catalyst, what will happen? This reaction goes out with this path. This is the activation energy, and once we use the catalyst, the reaction goes in this path. That means it is having less activation energy. This reaction required less activation energy. So in the presence of catalyst, less activation energy is required and the reaction occurs very fast. Okay, this is the path with catalyst and this is the path without catalyst. You can see this reaction taking place faster. Okay, and here are some characteristics of a catalyst. That catalyst generally fasten the reaction, it does not actually initiate the reaction. Okay, it fasten the reaction by decreasing the activation energy. Okay, you can see that in the if the activation energy is lower, then reaction becomes fast. Then after, it does not alter the delta G of a reaction, that means gives free energy of a reaction. Okay, whatever the gives free energy for a reaction without using catalyst will be same as the gives free energy using a catalyst in a reaction. Then after, a catalyst can catalyze a spontaneous reaction, that means it cannot initiate a reaction. एक रिएक्शन हो रही है तो उसको ये फास्ट कर सकता है, लेकिन कोई रिएक्शन नहीं हो रही उसमें कैटलिस्ट डालने से वो रिएक्शन स्टार्ट हो जाएगी, ऐसा नहीं हो सकता. दैट मीन्स जो स्पॉन्टेनियस रिएक्शन जो पहले से चल रही है उन रिएक्शन को तो जो कैटलिस्ट है वो फास्ट कर सकता है, लेकिन किसी रिएक्शन को इनिशिएट नहीं कर सकता. एक और बात, कैटलिस्ट एक और हेल्प करता है, इट हेल्प्स टू अटेन द इक्विलिब्रियम फास्टर. ओके, इक्विलिब्रियम जल्दी आ जाता है किसी भी रिएक्शन में अगर हम कैटलिस्ट यूज़ करते हैं. लेकिन अगर हम ये चाहें कि इक्विलिब्रियम ही चेंज हो जाए कैटलिस्ट से तो वो नहीं हो सकता. कैटलिस्ट डज नॉट ऑल्टर डिस्टर्ब द इक्विलिब्रियम. दैट मीन्स it helps in the reaction to move faster in forward as well as backward direction, okay, equally. Then after, the last topic of this unit, that is collision theory of chemical reaction. You know that according to this theory, it is assumed that the molecules are in the spherical form, okay, they are spheres, and the reaction occurs if and only if they collide with each other. If they do not collide with each other, reaction does not take place. Okay, भाई कंसिडर करो हमने एक सॉल्यूशन में दो रिएक्टेंट डाल दिए, लेकिन वो रिएक्टेंट जब आपस में एक दूसरे से उसके मॉलिक्यूल कोलाइड ही नहीं करेंगे तो उसमें रिएक्शन होगी ही नहीं. सो ही कंसिडर्ड ए रिएक्शन, दिस इज यू कैन से प्राइमरी रिएक्शन टाइप, A plus B giving out product, and if A strikes with B, then only reaction takes place, and he modified Arrhenius equation as rate is equal to ZAB into E to the power minus EA upon RT. What is Z? Z is a collision factor, or you can say collision frequency. That means it provides the information about the collisions of A and B. Here it substitutes the value of A in the Arrhenius equation. Arrhenius equation was K is equal to A e raised to the power minus EA upon RT. Okay, now collision frequency. What is collision frequency? Collision frequency is the number of collision per second per unit volume. एक यूनिट वॉल्यूम में कितने collisions होते हैं एक सेकेंड में, that is called collision. क्या है? जो डिफरेंट पार्टिकल्स हैं उनके बीच में आपस में collision, that is called collision frequency. Okay, this is denoted by Z. Okay, जो हमने यहाँ पे Z लिया है वो. Okay, ये जो इक्वेशन है ये सिर्फ तब हेल्पफुल है जब हम लोगों ने एक, अभी मैंने बताया ना ये सिंपल रिएक्शन, हमने एक सिंपल रिएक्शन ली. इफ वी आर टेकिंग अ कॉम्प्लेक्स रिएक्शन देन दिस इक्वेशन इज नॉट इनफ. Okay, that complex reaction only takes place if two conditions are fulfilled by the molecules which are striking or which are colliding with each other. These two conditions are, the molecule should have sufficient kinetic energy. देखो, अगर वो particles हैं एक दूसरे के साथ कोलाइड करते हैं लेकिन उसकी इतनी एनर्जी से कोलाइड करते ही नहीं है कि रिएक्शन हो, मतलब उनके अंदर सफिशिएंट काइनेटिक एनर्जी नहीं है, जिसको हम थ्रेशोल्ड एनर्जी भी बोलते हैं. दैट मीन्स मिनिमम एनर्जी रिक्वायर्ड फॉर अ रिएक्शन टू अकर. ओके, वो नहीं है तो वो जैसे धीरे धीरे ऐसे टच हुए तो ऐसे ही दूर हो जाएंगे, उनके बीच में रिएक्शन होगी. सेकेंड थिंग, proper orientation should be there, like particles are moving with proper frequency. Okay, but like this, if these are two particles, like suppose करो हमें ये जो पेन है इसको कैप लगानी है, बंद करना है इसको. These two are molecules, one molecule and this is second molecule. If they are having if they are not having sufficient kinetic energy, then अगर हमने इसको सही भी लगा दिया तो वहीं जाकर रुक जाएगा, वो अच्छे से बंद ही नहीं होगा. अगर इनके अंदर सफिशिएंट काइनेटिक एनर्जी है लेकिन अगर इनकी ओरिएंटेशन सही नहीं है, लाइक हम लोगों ने ऐसे ओरिएंट किया इनको कि ऐसे आपस में स्ट्राइक हो रहे हैं, ऐसे आपस में स्ट्राइक हो रहे हैं, ऐसे आपस में स्ट्राइक हो रहे हैं, तो ये कभी भी बंद नहीं होगा. ठीक है, ये कब बंद होगा? जब इनकी ओरिएंटेशन बिल्कुल प्रॉपर हो, एक सही डायरेक्शन में वो दोनों एक दूसरे से स्ट्राइक करते हैं. ओके, सो ऐसा ही मॉलिक्यूल्स में फॉलो होता है. एंड फॉर दैट जो इन दोनों अमाउंट मतलब दोनों ही कंडीशन को फुलफिल करते हैं, ऐसे कोलिजन को बोलते हैं हम इफेक्टिव कोलिजन. ओके, दैट कोलिजन इज कॉल्ड इफेक्टिव कोलिजन. ओके, एंड वो इफेक्टिव कोलिजन की कितनी प्रोबेबिलिटी हो सकती है किसी रिएक्शन में, उसके लिए एक और नया फैक्टर आया जिसको बोला हमने प्रोबेबिलिटी फैक्टर। ओके, दिस इज ऑल्सो कॉल्ड स्टेरिक फैक्टर। तो ये गिवन है पी से, एंड दिस ऑल्सो इंक्लूड्स रेट इज इक्वल टू पी जेड ए बी इंटू ई रेट माइनस ई ए अपॉन आर टी। ये पी जो है प्रोबेबिलिटी फैक्टर जिससे कि इफेक्टिव कोलिजन होते हैं वो इसमें इंट्रोड्यूस किया गया बाद में फॉर ए कॉम्प्लेक्स रिएक्शन। इसको कुछ डायग्राम से भी कर सकते हैं हम। जैसे मान लो ये कोई मॉलिक्यूल है और ये दूसरा मॉलिक्यूल है, इसमें आपस में रिएक्शन हो रही है। अगर वो दोनों एक दूसरे के साथ स्ट्राइक करेंगे वेरी स्लोली, देन नो रिएक्शन टेक्स प्लेस। अगर इस मॉलिक्यूल को ये जो पार्ट है ना, इसको इसे स्ट्राइक करना था, लेकिन ओरिएंटेशन कैसी है कि ये वाला जो पार्ट है, ये वाला जो पार्टिकल है ये इसकी साइड में है, तो भी ये रिएक्शन नहीं होगी। देखो नो रिएक्शन। अगर ओरिएंटेशन प्रॉपर है, देखो दीज आर द टू एरोज, ये याद रखना है, ये दो एरो हैं एक दूसरे की साइड। इफ ओरिएंटेशन इज प्रॉपर एंड प्रॉपर काइनेटिक एनर्जी इज देयर, लाइक ये वाला जो पार्ट है ये इसे स्ट्राइक करना है, हाँ बिल्कुल हो रहा है, और इनके अंदर सफिशिएंट काइनेटिक एनर्जी, देन आफ्टर दे रिएक्ट टुगेदर टू फॉर्म दिस प्रोडक्ट। ओके, दिस इज द बेस ऑफ कोलिजन थ्योरी, दीज आर द इफेक्टिव कोलिजन, दिस वन इज द इफेक्टिव कोलिजन। ओके, वन लिमिटेशन इज कंसिडर्ड फॉर कोलिजन थ्योरी। एक्चुअली बहुत सारी लिमिटेशन है थोड़ी थोड़ी, लेकिन हमें जो पढ़नी है वो मेन लिमिटेशन ये है कि इसने जो पार्टिकल्स जो हैं उनको एक स्फीयर माना था, ना कि क्या माना, उनकी स्ट्रक्चरल एस्पेक्ट्स की, किसी तरह की उनकी स्ट्रक्चर उसके ऊपर बात की। इसने जो कोलिजन थ्योरी थी इसने सिर्फ उसको स्फीयर माना था। ये इसकी एक लिमिटेशन में आती है, और इसकी लिमिटेशन कैसे दूर होगी वो फर्दर क्लासेस में पढ़ना है। ठीक है, तो ये यूनिट यहाँ पे ख़त्म होती है, केमिकल काइनेटिक्स। थैंक यू।